Hi everybody, welcome back. This chapter we've been talking about torque and we just got into recently angular momentum. And in our previous chapters when we talked about linear momentum, we then got into collisions. Well, now we're going to be getting into angular or rotational collisions. But it's really no different. The assumption is still the same. That is, the initial momentum, let's see if I can go full screen here, momentum initial, going to be equal to the momentum final, assuming there are no other outside forces or outside torques applied to the system right here. So you could say the momentum, let's see, we have the record right here and a turntable right there. So the momentum of the record initial plus the momentum of the turntable initial. By the way, this is going to become zero, right? Because the record isn't spinning. But when the record drops down the spindle onto the turntable, it's like a collision. It's like the momentum of the turntable gets the record up to speed so that it actually spins with the turntable. And so that's going to be equal to the final momentum of that system. So it's going to be the combined moment of inertia, because we know that momentum at any one point equals a moment of inertia times the angular speed. Okay, so it's going to be the combined moment of inertia. Kind of like we said before, it was the mass of the system. This is going to be the moment of inertia of the system times their combined angular speed. So that's the idea. All right, this is just sort of like a conceptual idea right here. But leading up to this point, we've been talking about things like merry-go-rounds. All right, and if you run straight at a merry-go-round, or maybe not straight at it, but maybe tangent to a merry-go-round and hop on, it's going to start spinning. Well, our example we're going to do in this segment is going to be on just that. All right, so we've got a child. This is from overhead now. This is just a regular playground spinning disc, as it were, merry-go-round. It has some handles on it, but a child runs towards it with a straight velocity. The child has mass, therefore the child has momentum, and then hops onto the merry-go-round. It causes the merry-go-round child system to have a shared angular momentum. All right, so we're gonna find out what that is. We're gonna solve for it. Actually, we're gonna solve for the angular speed of the system, but it's using the assumption that the initial angular momentum of the system is going to be equal to the final angular momentum of the system, assuming no other forces. Okay, so mass. Let's just write down some of the things that we know. And by the way, I'm going to need to shrink this down a little bit. So actually, I'm going to shrink it down a lot because I'm going to need a little more space. All right, how about like that? I think we can still read it. Okay, so the mass of the child, MC, equals 34.0 kilograms. Okay. The initial velocity of the child, VI, see right there, equals 2.80 meters per second. I wrote an 8, that is not a 2. 2.80 meters per second, all right, and tangential to the rim of the stationary merry-go-round. Okay, so the child is running at right angles to the rim, or you might say at right angles to the radius, which is very helpful. Not that any other angles are that much more difficult, but a right angle makes things kind of multiply out a little bit more easily, as we'll see in just a minute. The moment of inertia. Okay, so the I of the merry-go-round is 512 kilogram meters squared. All right, 512 kilogram meters squared, and the radius of the merry-go-round equals 2.31 meters. All right, so the child has momentum. The child has linear momentum that we call P. All right, well, that's going to translate into a final momentum of the system. All right, and the assumption here is also, we're making a couple different assumptions, that the child stays at the outside. The child kind of jumps on right here and then just holds on to the outside edge, or holds on to that rail right there, which is at the outside edge of their merry-go-round. Okay, so let's find out what the final angular speed of the system is after it begins rotating. Okay? Well, our assumption, once again, is that total linear momentum initial, angular momentum initial equals total linear angular. Sorry, I'm seeing that L and wanting to say linear. It's angular momentum final. All right. Of course, P, this right here, this is our linear momentum, and we kind of have a description for that. Well, this means then that the angular momentum of the child plus the angular momentum of the merry-go-round has to equal the angular momentum of the system after that collision. All right? Momentum is conserved, and so all the momentum initial has to add up to all the momentum final. Well, initially, the momentum of the merry-go-round is 0, right? Because it's not moving, and so we can cross that off. So we're going to say, all right, well, the linear momentum, I'm going to keep saying this. It's the angular momentum, but I keep wanting to say linear because it's L. The angular momentum of the child, therefore, is going to be equal to the angular momentum of that whole child merry-go-round system after the collision, all right, or after the child has jumped on right there, all right? Well, the linear, I did it again, the angular momentum at L. I need to get out of the habit of doing that. The angular momentum of the child. We describe that as the linear momentum of the child times what? How do we take a linear quantity and turn it into an angular quantity? Well, we multiply it by the radius, right? So that's going to be momentum of the child times R equals the angular momentum of the system. Okay? So that means that the system has angular momentum, which is going to be equal to moment of inertia of the system times the final speed, angular speed of the system. All right, this is kind of our rotational analog to mass times velocity, right? We said that that momentum, P equals mv, draw this up here. Linear momentum equals mass times velocity. Well, this is the rotational analog to that. Moment of inertia is mass. Angular velocity is like I said, the analog to velocity in rotational terms. Okay? Well, this is what we're solving for right here, so that's good. And I think we can figure out what the initial momentum of the child is, and we know what the radius is. But what would the moment of inertia of the system be right here? Let's write this out in a little bit more detail and make some sense of it. So that is the linear momentum of the child times the radius equals what? Well, we have the moment of inertia of the merry-go-round. That is 512. In fact, I'm going to write it in general terms. The I of the merry-go-round, which is a value that we're given. Plus, we need to take into account the moment of inertia of the child. All right, and so here we have a mass at some distance radius from the center right there. All right, and so that mass is going to stay at the edge. So this is the child right there. All right, what will the moment of inertia of that be? The moment of inertia, remember, is the sum of all the masses at radii squared, right? So we can think of this child as being kind of a point mass right here. And so their moment of inertia, the moment of inertia of the child, I think I'm writing it in black here, I'll be back in red. The moment of inertia of the child, when that child hops on the merry-go-round, is going to be the child's mass times a radius, the mass is from the center, squared. Okay? So they're going to be on the outside edge, and so their radius is going to be what the radius of the merry-go-round is. So we need to add that to the moment of inertia of the merry-go-round, right? So plus, I'll write it in the way we wrote it. So the moment of inertia of the child is mr squared. And multiply that by the angular speed of the system, which is what we're solving for. All right? So we have pretty much everything now. We have the mass of the child. I should probably have written a little c right there, mc of the child, times the radius squared. We know the moment of inertia of the merry-go-round. We know the radius of the merry-go-round. And we know the mass times velocity of the child. Let's just rearrange it and solve for the angular speed of the system. All right, so the angular speed of the system is going to be momentum of the child, let's see, times the radius divided by the moment of inertia of the merry-go-round plus the moment of inertia of the child, which we just figured out to be mr squared. Oops, you know what? I should be more specific. Mass of the child, right? Mass of the child times radius squared. All right. Well, I don't think we need to rewrite this, but we know that momentum, linear momentum of the child is mv, right? So it's mass of the child times velocity of the child times the radius divided by moment of inertia of the merry-go-round plus mass of the child times radius squared. Now we can plug in and solve for it, okay? And you know, I think I just got done saying I'm not going to rewrite this, and there I went and go ahead and I rewrote it. That's all right. Mass of the child, 34. Okay, right? 34, I should write 0.0. 34.0 times velocity of the child, that's 2.80 times the radius squared. The radius of the merry-go-round is 2.31 squared. We're going to divide that all by the moment of inertia of the the sum of the moment of inertia of the merry-go-round, which we are told is 512. So the sum of 512 plus mass of the child times the radius that the child is from the center of the merry-go-round squared, right? So that is going to be an extra little set of brackets in there. Mass of the child is 34.0 times the radius 2.31 squared. There we go. I think we have a complete equation now. So the angular speed of the system is what? According to my calculations, I get an angular speed of the system of 0.7. Let's see how many sig figs we have. Mostly 3, right? 0.733. What is it? Radians per, RAD per second. That's the final answer that I get. If you get something different, maybe I messed up. But that's what I got, and I think my answers are accurate. So this is collisions. And the assumption, once again, is the fact that the initial momentum of the whole system, all the different parts of the system, like right here, is going to be equal to the final momentum of the system because momentum is conserved. All right, so that's example 11-15, a good application of conservation of momentum, especially in rotational collisions. And that's it. See me if you have any questions, and I'll see you on the next one.